Hello everyone, greetings from VNR VIGNANA JYOTHI Institute of Engineering and Technology. This is Manohar Reddy, Department of Cybersecurity, Data Science and AADS. In this session, I am going to explain you the concept of Dijkstra Shortest Path Routing Algorithm. So in Dijkstra algorithm is a shortest path algorithm. We can use it to finding the shortest distance from source to destination. So in the network, there are number of nodes are traveling from source to destination, right? So in that, each and every node having certain distance to travel from the source to destination. So each and every node maintains the node information of itself as well as the neighbor node information itself. So here, the Dijkstra algorithm maintains all that nodes information as well as the routes information. So because of that, Dijkstra algorithm is the shortest path algorithm used to find the shortest distance from source vertex to all other vertices. Source vertex to all other vertices in a weighted graph. In a weighted graph, which contains weighted graph contains what? Each and every graph vertices as well as that weights of each and every graph, each and every edges. It works only when the graph has non-negative edge weights. So it works only when the graph has non-negative edge weights. That means only the positive edge weights are there, then it works. Then we can able to find the distance between the first vertices to second vertices or first vertices to end vertices. So to do this, Dijkstra algorithm provides a graph theory and it provides in the computer networks with the algorithm of shortest path algorithm. So it is a popular shortest path algorithm used in graph theory and computer network. And it finds the shortest path from single source vertex to all other vertices. So single source vertex to all other vertices. So if you see, these are all these vertices, these are all the vertices. From each and every vertices to another vertices, we can find the distance. But even though the distance is there, but out of all the distances, it finds the smallest distances. It finds the smallest distances. So this weighted graph contains the weights, vertices and the distance of each and every vertices differences. And it was developed by Dijkstra W. Dijkstra. So Dijkstra W. Dijkstra. As the name itself, this algorithm, this shortest path algorithm is named as Dijkstra algorithm. This algorithm is widely used in computer networks, GPS and navigation systems. So nowadays we are seeing real-time applications in the Google Maps which you want to go from source to destination. It finds several routes. Out of that all the routes, it finds the best path, suitable path, shortest path. And routing protocols. In the routing protocols also, we are using this algorithm to find the each and every node distances. And transportation systems. In the transportation system also we are using how it finds the shortest distance, network optimization and robotics and path planning. So these are all the different application areas that you are going to use this shortest path algorithm, Dijkstra algorithm. So important terms we have to remember this in this graph algorithm or in this shortest path algorithm. The first one is what? Vertex or node. So vertex or node. These are the vertex or nodes. So a point in the graph is called as vertex or node. And the edges, connection between two vertices. Connection between two vertices. These are the connection between two vertices is called as edge. And the weight, cost or distance associated with an edge. The cost or weight associated with these distances, this edge. So that is the cost weight. Because of these weights are there, it is taken as a weighted edge, weighted graph. We can take it as a weighted graph. The source is nothing but what? Starting vertex. So from which is the source? So here in this diagram we are showing that 2 is a source. So that is the starting vertex. And the distance, shortest known distance from source. So we can able to find each and every distances from the source. So 2 to 0 is one distance, 2 to 1 is one distance. So if you have more than 3 or 4 nodes, we can find a possible number of ways to find the shortest distance from source to destination. And visited, vertex whose shortest distance has been finalized. So the visited is nothing but, visited edge is nothing but, visited vertex is nothing but the whose shortest distance has been finalized. Suppose if you see, for suppose 2 to 0, the 6 is the direct connection, direct graph. But if you go 2 to 1 or 1 to 0, the distance is what? 3 plus 1, 4 only. So 2 to 0. To reach the 2 to 0, we have to go through 2 to 1, 1 to 0, because it is the smallest distance. So here the vertex whose start distance has been finalized is what? Visited. So this one is visited node. And how it works, shortest path algorithm, how it works to find the shortest distance between the two or more nodes. So first, initially we have to select the node with the smallest distance. We have to select the node with the smallest distance. So we have to find the select the smallest distance. Select the node with the smallest distance. And the second one is what? Mark it as a visited. So marks it as a visited. When you want to reach 2 to 0, you need to mark this one as a visited and check all its neighboring nodes. Check all its neighboring nodes. Calculate the new possible distances. If this is the diagram for with the three vertices, if you see with the 5 vertices or 6 vertices, you may check the number of neighboring nodes as well as check the number of possible distances. And updates the distance. If the new distance is smaller, you can update the distance. If the old distance is smaller, keep it like that. But if your new distance is smaller, then update the new distance in the distance vector. And repeat the process until all the nodes are visited. Repeat the process until all nodes are visited. So this is the diagram. Consider the example on above. What are the edges? What are the vertices? So here the vertices are what? Vertices are 0, 1, 2. And edges are what? Edges are 0 to 1 and 0 to 2 as well as 1 to 2. Right. So now we have to construct a cost matrix. We have to construct a cost matrix. So what is the cost matrix? So cost matrix represents the distance of each and every node of each and every edges. So 0, 1, 2. So what is the distance between 0 and 0? So 0 and 0 is nothing but self distance. It is a 0. And what is the distance between 0 to 1? 0 to 1 distance is what? 1. So we need to keep it as 1. And 0 to 2 distance is what? 6. And again 1 to 0. 1 to 0 is distance is what? Only 1. And 1 to 1 is a self distance. 1 to 1 is what? 0. And 1 to 2 is the distance is what? 3. And similarly take the distance for 2 also. 2 to 0 is what? Distance is 0. And 2 to 1 the distance is what? 3. And 2 to 2 the distance is what? 0, because it is a self. So now edges are what? 0 to 1, 1. So here 0 to 1, 1. 1 to 2, 3. 0 to 2, 6. So this is the cost matrix. This is the cost matrix. But out of this all the cost matrix, if you see the diagram, to reach the 0 to 2, we have to go through 2 to 1 or 0 to 1 or 2. Or else because of the source is 2, 2 to 0 is distance is what? 6. To reach the 0 as a destination, we need to reach 2 to 1 and 1 to 0, because the distance between these nodes are very small. So now we have to calculate for each and every node like that. So now after seeing this diagram, the source node 2, initial distances from 2 to 0 is what? Infinity. 2 to 0 is what? Infinity. So because 2 to 0 is not there. 2 to 0 is what? 6 here. So 2 to 0, 2 to 2 is what? 2 to 2 is what? 0. 2 to 0 is what? 6. And 2 to 1 is what? Infinity. 2 to 1 is what? Infinity. So here 2 to 2 is what? 6. 2 to 0 is what? 6. 2 to 2 is what? 0. 2 to 1 is what? Infinity. 2 to 1 is what? 3. Right. So now initial distances are what? This one. So now we need to find these distances. Node 2, from node 2, node 0 is what? The distance. Node 2, 0 is what? We need to calculate the smallest distance, right? So to find that smallest distance, node 2 to 0 is what? Infinity. Node 2 to 1 is what? Infinity. And node 2 to 2 is what? 0. So now we need to calculate the node 2 to 0 as well as 0 to 1. We need to calculate. So before calculating the from node 2 to 0 is what? 6. 2 to 1 is what? 3. So therefore node 0 contains node 0, 1, 2 and the distance is what? 6, 3, 0. 6, 3, 0. So from node 2 to 0, see here the node 2 to 0 is what? 6. And node 2 to 1 is what? 2 to 1 is what? 3. 2 to 3 is what? 6. 2 to 1 is what? 3. And 2 to 0 is 2 to 2 is what? 0. Right. So next node 1 is selected because it is the distance is what? 3. Through the node 1, 2 to 1, 1 to 0. So 2 to 1 is what? 3 plus 1 to 0 is what? 1 to 0. See here. 1 to 0 is what? 1. 1 to 0 is what? 1. So 1. 3 plus 1 equals to 4. Since 4 is less than equal to 6, the distance to node 0 is updated to 4. Distance to node 0 is what? Updated to 4. So we need to update. After updating the shortest distance from source node 2 to other nodes, 2 to 0, 2 to 1, 2 to 2 is what? 2 to 0 is what? 4, 2 to 1 is what? 3, 2 to 2 is what? 0. So take example 2. The 2 from 2 to 0, 2 to 0 is what? 4. Now 2 to 1 is what? 3. Right, and 2 to 2 is what? Same. And remaining 0 to 1 is what? Same as usual. Same 0 to 1 as usual. The distance is what? 1. 0 to 1, 1. So like the way you can update the shortest distance after finding the shortest distance from source to destination, update the table, update the values, update the graph. So like the way you can find the shortest path between the source node to destination node. When you have more number of vertices, more number of edges, then you can have more number of possible ways to find the shortest distance. See another example. If you see another example, there are 5 number of vertices are there. 5 number of vertices are there, and along with that 5 edges are there. 5 edges are there. So the distances of each and every one. See, the source is what? 0. If source wants to reach the destination 3, what is the minimum path? If source wants to reach the destination 4, what is the minimum cost? So now see here, for 0 to 1, the path is, the weight is what? 4. 0 to 4, we need to calculate. So construct the cost matrix. Construct a cost matrix. 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. Now 0 to 0 is what? The self distance is what? 0. And 0 to 1 is what? 4. And 0 to 2 is what? 8. And 0 to 3 is not directly connected, so we can take it as infinity. And 0 to 4 is also not directly connected, so it taken as infinity. Similarly for 1. 1 to 0. 1 to 0, the cost is what? 4. And 1 to 1 is what? 0. And 1 to 2 is not directly connected, so 1 to 2 is what? Infinity. Similarly 1 to 3 is also not connected directly, so infinity. The next 1 to 4 is not directly, 1 to 4 is directly connected, and the distance is 6. Similarly for 2. So 2 to 0 is what? The distance is 8. 2 to 1 is not directly connected, so it is infinity. And 2 to 2 is what? Self distance 0. 2 to 3 is what? 2. And 2 to 4 is what? Not directly connected, so it is infinity. Similarly for 3. 3 to 0 is not directly connected, so infinity. 3 to 1 is not directly connected, it is infinity. 3 to 2 is directly connected with the distance 2. 3 to 4, 3 to 3 is self distance, it is 0. And 3 to 4 is directly connected, so distance is what? 10. And similarly for the 4 also. 4 to 0 is not directly connected, so infinity. 4 to 1 is directly connected with the distance is 6. 4 to 3 is directly connected. 4 to 2 is not directly connected, so takes infinity distance. And 4 to 3 is directly connected with the distance 10. And 4 to 4 directly not connected, so it is self distance. So it is a 0. Now we need to calculate what? We need to calculate the shortest distance from 0 to all other nodes. 0 to 1, 0 to 2, 0 to 3, 0 to 4, we need to calculate. So for 0 to 1, the minimum distance will be 4 as usual. So there is another no route is available. If you want to go like this also, if you see 8 plus 2 plus 10, 10 plus 10, 20, 20 plus 6. So 26. So compare with the 26, 4 is the less number. So to reach the 0 to 1, the weight value is what? 4 only. So 0 to 1 shortest distance is what? 4. Next, similarly 0 to 2. So to reach the 0 to 2, the smallest distance is what? If you go through like this, 0 to 1, 1 to 6, 1 to 4, 1 to 4, 4 to 3 like this. To reach this 2, 4 plus 6, 10, 10 plus 10, 20, 20 plus 2, 22. So to reach 2, 22 is the distance. But here 8 is the distance. So smallest distance is what? 8 only. And similarly for 3. So for 3, 0 to 2, 2 to 3. So 8 plus 2, 10. From 0 to 1, 1 to 4, 4 to 3. If you see 4 plus 6, 10, 10 plus 10, 20. So 20 will takes to reach the 3 through 1 and 4 nodes. So comparing these two, the smallest distance from 0 to 3 is what? Via 2. So 8 plus 2, that is the smallest distance. That is nothing but 0, 10. And similarly for 0 to 4. So to reach the 0 to 4, what is the smallest distance? If you go like this, 0 to 2, 2 to 3, 3 to 4, 8 plus 2, 10, 10 plus 10, 20. So to reach the 0 to 4 through 2, 3, the distance is what? 20. But if you go 0 to 1, 1 to 4, the distance is what? 4 plus 6, 10. So 0 plus 4, 10. So now these are all the shortest distance values from source node 0, from source node 0 to all other nodes. All other nodes like 0 to 1, 1 to 0 to 1, 0 to 2, 0 to 3, 0 to 4. So now after that update the values. After that update the all values. See here the 0 to 1 updating all these values. What are those values? Now updated values are 0, 4, 8, 10, 10. These are all the updated values from source 0 to remaining all the nodes 0 to 1, 1 to 0 to 2, 0 to 3, 0 to 4. So these are the distance values from source node 0 to remaining all other nodes. So like the way the shortest path algorithm, even number of ways are there. If you see number of vertices, number of edges are there, then you can find multiple ways, multiple paths. So out of that all the paths, suitable path you have to choose. So that is the Dijkstra algorithm main importance. So the final output values of 0 to all nodes are 0, 4, 8, 10, 10. 0, 4, 8, 10, 10. So that is what we seen in this diagram. After constructing this cost matrix, after finding the shortest distance, after updating the values, these are the final outputted values 0, 4, 8, 10, 10. Advantages of this algorithm. So it is simple and easy to understand because we no need to calculate anything, right? We have to see the each and every distance from each and every vertices and find the distance of each and every one, compare the distances from one path to another path. And the second one is what? Efficient for finding shortest path. Obviously it is because if there is a less number of ways, the less number of vertices, less number of edges, the finding shortest path is very easy, right? Efficient for finding shortest path and useful for network routing also. It works well with the non-negative edge weights. So we have seen the two examples with the not negative edge weights. So if we have negative edges weights, then it won't works properly. And it can find shortest path from one source to all other vertices. So because of that one, we can find all the distances for all the vertices. Even though the vertices have certain distance, we can calculate the smallest distance and compare with the distance. If the finding distance is smallest one, then update the smallest distance in the original distance place. And the limitations are what? It cannot handle negative edge weights correctly. So that's what I am telling. The negative edge weights are not properly calculated, not properly finding. And it can be inefficient for very large graphs. So if you have very large graphs like with 10 edges, 20 edges are there, it is very inefficient for finding the implementation of shortest paths and array point of view. And it is a primarily single source shortest path algorithm. It is primarily on single source shortest path algorithm. So these are all the how to find the shortest path algorithm and why it is important for finding the shortest path algorithm and advantages and limitations of the shortest path algorithm. I hope all of you understand. Thank you all.